In this lecture, we will study the combined effect of bending and torsion on the shaft, right? In practical applications, shafts are subjected to three types of load. Shafts are subjected to three types of load. These three types of load are bending moment M, torsion T, and axial load or axial force. Bending moment M or bending stress on the shaft, it acts along the longitudinal axis of the fiber. If we're talking about the bending moment, then bending moment we take in about the neutral axis of the shaft, which is taken along the cross section of the shaft. And torsion moment, turning moment, it is taken about the axis of rotation of the shaft, and axial load, it is applied along the centroidal axis, along the axis of rotation of the shaft, right? If we study the direction of these three forces, then say this is our shaft, right? This is our shaft. This is the axis of rotation. This is the axis of rotation, clear? And this is the neutral axis, right? This is the neutral axis of the shaft, clear? Now, if we apply torque T here, the turning moment will be, direction of turning moment will be in the direction of this way. This turning moment T is trying to rotate this shaft about its axis of rotation, which is along the length of the shaft, clear? And what will be the effect of bending moment? Bending moment will try to rotate the beam turn the beam about neutral axis, right? About the neutral axis. How it come? We know that, suppose here is a fiber, right, a layer. If we get this 3D layer from here across the length, then it will be like this one, right? Suppose at the cross section, suppose this is a layer, at this layer shear stress will be along this direction, right? It will be along this direction, and bending stress will be along this direction, right? Because bending stress always try to elongate the shaft or shorten the shaft, and shear stress here generated will try to twist the shaft about its axis of rotation, right? Shear stress will try to twist the shaft about the axis of rotation. If we study these things by the force generated by these stresses, then say elemental area of this layer at distance, say it is at distance smaller from this centroidal axis, from this centroid, then the bending force generated will be sigma into dA, and shear force generated will be tau into dA, where dA is the area of cross section, right? Area of cross section for this portion dA, clear? Right? So this force tau into dA will try to turn the shaft about this axis of rotation. So moment is like this way. This is moving right this way, right? This way. Here, it will be like this way. Clear? Right. And neutral axis, this sigma into dA will try to, this sigma into dA force will try to rotate the shaft about neutral axis, right, in this direction, Clear? Now combined effect of these two we will study. Another force is axial load. It acts along the centroidal axis of the shaft, right? It acts along the centroidal axis of the shaft. Clear? Say this is the centroidal axis, then this here will be the force F. Clear? This will be the, it will be along this one. This is the, say, axial load Fa. Load axial, load acting along the axis of the shaft, and this, if we are saying that it is axial, that means this force is acting along the centroidal axis of the shaft. In general cases, during the analysis what we take, we see that this Fa, axial force, and this sigma into dA, they are parallel to each other. They are acting in the same directions, right? If it is a compressive one, then bending stress will be in the same direction. Here they are acting in opposite direction, but their line of actions are parallel to each other. So what we take, in this situation we take the resultant of these two forces, right? Bending stress and axial load. During the analysis what we take, the resultant of these two forces and shear force generated by this turning moment T, right? The effect of these two load is considered. Resultant load coming from this bending force and axial force, and another force is shear force due to this star T, right? Effect of these two forces are considered during the analysis of combined effect of bending and torsion, right? In this situation we are considering that there is no axial force acting on the shaft, right? There is no axial force acting on the shaft. See, there is no axial load. There is no axial load acting on the shaft, right? We will consider only these two effects of the load, right, during this analysis. Clear? Because in syllabus these two effect of these two load is considered, this one is not considered. But do recite that whenever in the analysis, when we will do there will be the same procedure which we are going to adopt for these two, right? Then in that condition two will be the resultant effect of this one and this one will be 1, and another force will be this one, right? But here we are considering there is no axial load, then we will go for the relation between bending moment and torsion for generating equivalent bending moment and equivalent torsional moment on the shaft, right? Now, from the principal stress analysis, right? Principal stress analysis, we know that principal stress generated when a body is subjected to more than one stresses, then there will be a maximum stress, maximum normal stress in the body, and there will be maximum shear stress in the body. Here the loading of shaft in this case will create a uni-axial stress system accompanied with a shear, right? The shear system will be like this way. This stress system will be like this way. Bending stresses acting along the length, longitudinal direction, and tau is acting along the cross section, right? Considering the positive directions, right? Then what will be the principal stress? Principal stress, by the definition of principal stress, we know it is equal to, so here sigma first is denoting major principal stress or maximum principal stress, right? Measure principal stress and or it is maximum, and sigma second it is denoting minor principal stress or it is minimum, right? This one is equal to sigma 1 plus sigma 2. These are the two normal stresses acting perpendicular to each other, right? Sigma 1 plus sigma 2 by 2 plus minus under root sigma 1 minus sigma 2 by 2 square plus tau square, right? Here sigma b is equal to sigma 1 given, and sigma 2, there is no sigma 2, it is not a biaxial stress system. So for uniaxial stress system we know that sigma 2 is 0 here, there is no sigma 2, then sigma 2 will be 0. This formula is basically we have derived when we are studying principal stresses. For biaxial stress system accompanied with shear, it is uniaxial stress system, so sigma 2 will be 0 and sigma 1 is equal to sigma b. Put this value here, then value coming is sigma b by 2 plus minus under root sigma b by 2 square plus tau square, right? This is the maximum principal stresses or minimum principal stresses generated in the shaft. Clear? Now both side multiply by pi by 32 into d cube, where d is the diameter of the shaft. So this is equation 1. 2 into d cube to both sides, right? Then what will happen? Equation will come to sigma, and see we are deriving the expression for maximum principal stresses, right? When we are considering maximum principal stress generated in the shaft, considering maximum principal stresses generated in the shaft, considering, right? Then sigma first into pi by 32 d cube equal to sigma b by 2 into pi by 32 d cube, and plus minus, sorry, there will be no minus, clear? Take no minus, it is plus under root sigma b into pi by 32 d cube square plus tau into pi by 32 t cube square, right? This is expression will come like this way. Now we know that pi by 32 d cube is equal to zp, so it can be written as sigma first into z for section modulus, and sigma b by 2 into z, right? And plus here it will be sigma b, this is sigma b by 2, right? Sigma b by 2 into z plus whole square plus tau into, this will be equal to zp by 2, right? Here because pi by 16 into d cube is zp, that is polar modulus, right? Now we know that sigma 1 into z, that the sigma 1 Sigma first is maximum principal stress into section modulus here will be equal to, say it is equal to ME, that is equivalent bending moment set up in the beam due to the equivalent bending moment set up in the shaft due to the combined effect of bending and torsion, right? And sigma B by 2 into Z will be equal to M, that is the bending moments set up due to bending only, right? Due to bending only. And this is bending set up in the shaft due to the combined effect of bending moment and turning moment, right? M plus under root M by 2, this is M by 2 is square plus T by 2 square, right? Sigma M into Z equal to M. Now this whole expression will be equal to M equal to M plus under root M square plus T square divided by, sorry, this will be here, this one divided by 2, right? This is the expression, right? M equal to M plus under root M square plus T square divided by 2. Clear? Now we will generate expression for turning moment, effective turning moment T. The same way we know. Now I am writing the expression again, that if we write the expression for both equivalent bending moment for both maximum and minimum principal stresses, then it can be written as M plus minus under root M square plus T square upon 2. Clear? Depending upon which one is given, it is, if minor principal stress we are going to calculate by the help of these equations, then you will go for M equal to M minus under root M square plus T square by 2. If there is maximum principal stress given in the problem, then you will go for M equal to M plus under root M square plus T square upon 2. Now we know that by principal stress, by the maximum shear stress equations, we know that the value will be tau max equal to, that is maximum shear stress. If we, by the definition for biaxial stress system, if we write the equation for maximum shear stress, then it is equal to sigma 1 minus sigma 2 by 2 whole square plus tau square, right? Clear? Here sigma 2 is 0, sigma 1 is equal to B, right? And multiply both sides by pi by 32 d cube, then expression will be tau max into pi by 32 d cube. And here in the equation will be sigma B by 2 into pi by 32 d cube square plus tau into pi by 32 d cube square. Clear? Tau max pi by 32, this is equal to T E by 2. Clear? And this will be equal to sigma B into Z. Sigma B into Z will be equal to M by 2, and tau, this will be equal to T by 2 into ZP, right? Sorry, tau into ZP upon 2. Then we can write the equation again. This will be equal to M by 2 square plus T by 2 square. Clear? So if we further simplify it, then this will be equal to T equal to under root M square plus T square. This is the required expression for if equivalent turning moment due to the combined effect of bending and torsion. Right? What is T? T is equivalent turning moment or twisting moment. Turning moment. And what is ME? Here ME is equivalent bending moment. Right? So during combined bending and torsion, we calculate equivalent bending moment and equivalent turning moment set up in the shaft due to the bending moment and torsion applied on the shaft. This is all about the combined effect of bending and torsion.